check on was the final projects. So does everybody, so remember that you have to either do a final project or do some problem sets if you're taking this course for credit. If you're taking it for a grade, you have to do all those things. And I just want to check that everybody has a topic. Does everybody have a topic? Who's going to do one? You don't have a topic?
Oh, I'm doing.
You do have a topic. Does anyone not have a topic? Who's going to do one? Okay, good. If you need to talk, if you want to talk about references, then come find me in my office anytime. I know I've talked to a few of you. If you already have your favorite references, then great. If you're doing a topic that I know nothing about, I'll try to help with references. Just stop by anytime. Okay, any questions about this now that it's sunk in? Okay, so I want to give some somewhat qualitative explanation of asymptotic symmetries. So I'm just going to spend probably half an hour on this. This is a huge topic that there's a huge amount of literature on. There's lots of current work on it. I just want to give some flavor, so I won't go into much detail. The starting point is the fact that so similar expressions, meaning like the energy and the angular momentum that we've been talking about, there are similar expressions for all the generators of the Poincare group. In 4 dimensions, well, in general, the Poincare group is the Lorentz group, and together with the translations. So, for example, in 4 dimensions, this group is sometimes called ISO31. Lorentz group is SO31. The I is just there to remind you that there are translations. This is Lorentz. Semi-direct product. Translations. If we call the Lorentz transformations M mu nu for boosts and rotations in the mu nu directions, and the translations P mu, then there are 6 of these and 4 of those, so there are 10 generators of the Poincare group in 4 dimensions. If we label all the generators, so let's take the whole set of 10 of them and call those VA, where A is 1 to 10. So each VA, each generator of the Poincare group, is associated to some vector field zeta, which corresponds to that generator. So the translations are just the 4 unit vectors in 4 directions, and the rotations are the usual rotation generators and boost generators. So there's 10 of these vector fields, which under Lie brackets, zeta A, zeta B, under Lie brackets is given by the structure, given by the Poincare Lie algebra FABC zeta C. So these give you a representation of Poincare. Now, in the Hamiltonian formalism, we say the words charges generate the symmetries. So what that means is that the conserved charge H associated to a symmetry zeta acts under Poisson brackets by doing the symmetry transformation. Okay, so this is a general feature of Hamiltonian mechanics. If you haven't studied Hamiltonian mechanics recently, then it's probably not terribly familiar. But you can think of this as just a definition. More accurately, in a theory with constraints, we can't really use Poisson brackets. So Poisson brackets, remember, are like the thing where P and Q have Poisson bracket 1. That doesn't quite work in theories with gauge symmetry. You have to solve the constraints and then do Poisson brackets. Or you can do, or equivalently, you can use Dirac brackets, which account for the constraints. For our purposes, and often this is how people actually think about it, we could just think of this as a definition. That we define the action of the charge on anything as generating the symmetry. So on the right-hand side is a Lie derivative. X here is anything made from fields. So it could be like the metric, or some curvature, or if there are other fields in the game, it could be some scalar field or whatever. So if you want the charges to act on the fields this way, then now you can ask what happens when you act multiple times. And we can act multiple times on the right-hand side. And for all that to be consistent, you need the algebra of the charges to actually be the same as the algebra of the symmetries. So consistency of this formula that I've written requires that H zeta A with H zeta B had better be equal to H of zeta A zeta B under Lie brackets. This is actually not quite required for consistency. You can have the addition of constants here, which actually does happen in interesting cases. These are called central charges, and they can show up in the charge algebra. So the point is that the conserved charges give you a representation of the symmetry algebra. This is always true. This is true like in E&M as well. I'll mention that example in a minute. In that case, the charge would just be the total global U1 charge, and this expression is basically trivial because there's just one charge and its commutator is 0 because the Lie algebra is U1 to be a. But more generally, there can be interesting commutators there. So this algebra that you get defines the asymptotic symmetry group. So another way of, well, this is the algebra. You have to exponentiate to get the group, but you can think of this as defining the infinitesimal parts of the group. So that another way that some people write this. So let's notice something important here, which is that when you calculate the conserved charges in GR, remember that it's just an integral out at infinity, right? Zeta was defined everywhere. You could act with a Poincare generator everywhere, but these charges only depend on the value of zeta out near infinity. So it's only the asymptotics of the symmetry generators that are actually showing up in these charges and in this algebra, so that's why it's called the asymptotic symmetry group. What that does is it sort of mods out by trivial diffeomorphisms. So sometimes people define it this way. It's the set of diffeomorphisms modded out by trivial diffeomorphisms. So let me define what I mean by this. So all diffs, that's just every vector field that's allowed. The trivial ones means those with h of zeta equals 0. So if you have diffs that vanish at infinity, diffs that are falling off, those are really pure gauge. Those are called trivial diffs. As I was talking about last time, those don't act on the states, they just give you some redundancy in description. So when you take this quotient, that's done automatically by these expressions that I've written here, because they only depend on the asymptotics of the vector of the generators of the vector fields. So the infinitesimal version of this group is the algebra of conserved charges.
Question? This is no longer the Poincare, right?
Sorry?
You started writing the Poincare generators and then set it at infinity, but this is more general than that.
Well, yeah, sorry. So that was a particular example. This can be defined very generally in flat space at spatial infinity. It's Poincare.
All diffs, mod trivial diffs is just Poincare?
Yeah. You thinking BMS?
Yeah.
I'll come back to that. That's because that's at scribe pulse.
I see. This is spatial.
This is spatial infinity. Yeah. Other question? Okay, so the asymptotic symmetry group is more general than just GR. It shows up in gauge theory. The simplest example, as I said, is in DNM. So this gives some good intuition for asymptotic symmetries. So electromagnetism has an infinite number of gauge transformations that you can do, right? Leveled by a function. You can do gauge transformations anywhere in the space-time. So those are the local U1. A mu goes to A mu plus d mu pure gauge or trivial transformations. And then there's global U1. So the global U1s, where you take, so we need some charged matter to talk about the global U1s. If you have some charged matter, then the gauge transformations also rotate the phase of the matter fields. And if you do that phase rotation everywhere, instead of just doing it locally with a function of x, then that's a physical or non-trivial transformation. So for example, in quantum theory, it's actually acting on Hilbert space. So E and M has an infinite number of trivial symmetries, all functions worth. But of course, just one conserved charge. Q, the total charge, which you can calculate from fields using Gauss's law. Okay, so the notion of this idea of asymptotic symmetry group formalizes what you already knew, which is that even though E and M has an infinite number of transformations you can do, there's only one conserved quantity. And that one conserved quantity you could think of as associated to the one physical transformation on the theory, which is the global U1. So the asymptotic symmetry group in this case is the algebra of the conserved charges, which is just, there's only one of them, so it's just the U1 global transformation.
So the global is a subset of the local?
Yeah, you can say that. People use different words. Sometimes when they say local, they mean local and dying off at infinity. Sometimes they don't. So it's, you sort of have to be careful about exactly. Yeah.
So here are we saying that even if we put this in a box or something with a boundary, none of the above will have an automatic generator on the boundary?
None of these?
Yeah.
Well, if epsilon dies off at infinity, they won't have any. If it dies off, if epsilon is 0 at the boundary, then no. But if epsilon is finite on the boundary, then it's got a global piece to it, and that one does have that one has the.
So even in that case, it's only the global piece.
Yeah, just the global piece will contribute because there's just this one charge. So now gravity. So in gravity, the ASG is often equal to the isometries of some background space, but not always. So for example, in asymptotically flat, as I was describing, you can check that when you impose the boundary conditions that say that the metric dies off at spatial infinity, the only diffeomorphisms that have finite associated charge, when you evaluate the Hamiltonian, the only ones that are finite at infinity are the Poincare charges, so the ASG is the Poincare group. Another example is that if you have asymptotic anti-de Sitter, boundary conditions in 4 or higher dimensions, then the ASG is the isometries of pure, that is empty, ADS-D, which is SO D minus 1, comma 2, the maximally symmetric spacetime. So like ADS4 has 10 generators that give you SO 3, 2. Now this also happens to be the D minus 1 dimensional conformal group. So what does that mean? Well, in the classical theory, it means that there's something about classical gravity and anti-de Sitter that respects the symmetries of the lower dimensional conformal group. In the quantum theory, if you say that same statement, it starts to sound stronger. So in the quantum theory, it means that the Hilbert space of quantum gravity and asymptotic ADS has to be organized into representations of the lower dimensional conformal group. So the states have to transform under the conformal group. And that's pretty much the definition of a conformal field theory in D minus 1 dimensions. So this is sort of one way of looking at the starting point. One way of thinking of the starting point of the ADS-CFT correspondence that relates gravity and ADS to conformal field theory in lower dimension. Just knowing the symmetries isn't enough for that, because you also have to worry about whether this is a conformal field theory in the usual sense, but it turns out the answer is that it is. So, as I think I explained at some point before, but let me repeat it, the asymptotic symmetries in gravity are necessary to have some conserved quantities, and they replace your usual intuition in terms of conserved charges coming from symmetries. In gravitational theories, conserved charges come from asymptotic symmetries. And it had to be that way because generic gravitational backgrounds have no symmetries. Once you add some matter, you're going to break all the symmetries. It's not translation invariant. It's not time translation invariant. It's not Poincare invariant. So the only way we could have had conservation laws in gravity is if we didn't actually require exact symmetries, and that's exactly what happens. We only require asymptotic symmetries to get conservation. Yeah.
Is that a fact of gravity or Gauss theory? Because you said the same thing about ENM.
Yeah, I guess you could say the same thing about ENM. Yeah.
So do all of these definitions have some background subtraction scheme that comes with them?
Yeah, they do. So like in asymptotically flat space, it's just it's pretty similar to what I described for the energy. In asymptotic ADS, there's different prescription.
Like for instance, what I was thinking was if you look at the local U1 transformation, instead of saying that epsilon dies off at infinity or is a constant.
Oh, that one doesn't need any kind of background subtraction.
So what if epsilon is not a decaying function at infinity, but it's like something that grows in